Welcome everybody to this new lecture of our paper number 3rd, Waves, Oscillations and Acoustics. In today's lecture, we will discuss yet another new topic of our syllabus, that is about superposition of two perpendicular harmonic oscillations having frequency ratio 1:2. Or you can say it the superposition of two perpendicular harmonic oscillations of different frequencies, because one harmonic oscillations which are perpendicular to each other have frequency ratio 1, that is you can say it n, and the other harmonic oscillation which is perpendicular to the first have frequency say 2n. That is the frequency ratio between the two harmonic oscillations which are perpendicular to each other are different. That is, they have different frequencies. This is our topic. And in our previous lecture, we were discussing about the topic that superposition of two perpendicular harmonic oscillations having equal frequencies. This topic. Superposition of two perpendicular harmonic oscillations having frequency ratio 1:1. That is, frequency is same. Frequency is same, but this time we have another topic in which two perpendicular harmonic oscillations have frequencies in the ratio of 1:2. That is, if one harmonic oscillations have frequency equals to 10 hertz, the other one has 20 hertz. And the basic thing is that these two harmonic oscillations are perpendicular to each other, not collinear. These two harmonic oscillations are perpendicular to each other and having frequency ratio 1:2. That is, if one has frequency equals to 50 hertz, the other one has 100 hertz. Okay, so the frequency ratio between the two harmonic oscillations which are perpendicular to each other has frequency ratio in the ratio of 1:2. This is our topic of today's lecture, and we will start it just that let us consider two SHMs perpendicular to each other having different amplitudes and phase and frequency ratio 1:2. These are three conditions. We have two SMHs which are perpendicular to each other and having different amplitudes and phase, different amplitude, different phase. That is, has phase difference between them, and frequency ratio 1:2. That is, if one wave, one SHM have frequency ratio is equals to 1 hertz, the other has 2 hertz, exactly double to the first. Okay, let the first SHM be along x-axis and the second along y-axis. That's why these are called as perpendicular harmonic oscillations, because if one SHM is along the x-axis and other is along the y-axis, and you know that x-axis and y-axis are mutually perpendicular to each other, since their frequencies are in the ratio 1:2, their angular velocities will be in the ratio of 1:2. Why? Because according to this formula, if one has frequency equals to n, then the angular velocity is omega, and if other has value frequency is double of first, then this is also double. That is, the angular velocity is also double. So why the frequency ratio between the two SHM is exactly same to the ratio of angular velocity of those SHM. So the displacement due to the SHMs at any instant t can be represented as this. Equation number first and equation number second. X equals to a sine omega t is the displacement equation of the first harmonic oscillation, which is travel into the direction of x-axis, and this is equation number second is the equation of displacement of the second SHM which is traveling along the y-axis. And look at here, amplitude A and here is amplitude B. That is, these two SHM have different amplitude and different direction. In the direction of x-axis, so y it is represented as x, and into the direction of y-axis, so y it is represented as y. Into the form of sine wave, that is why we use sine function, trigonometric sine function, and omega is the angular velocity. You understand by this fact that if the frequency of the two SHMs is in the ratio of 1:2, this implies that their angular velocity will also be into the ratio of 1:2. Okay, so why here is the angular velocity is omega, and here is, look at 2 omega. Time is same, and there is a phase difference between the two displacements. The phase difference is represented by phi. So this equation x is equals to a sine omega t, equation number first, represents the displacement of SHM into the direction of x-axis, and y is equals to b sine omega 2 omega t plus phi. This is equation number 2, represents the displacement of a simple harmonic motion or simple harmonic oscillations into the direction of y-axis. And you know that these two axes are mutually perpendicular to each other. That's why we use this two perpendicular harmonic oscillations. Okay, this. So this is equation number first, and this is equation number second. So we have from equation number first, what we have, that x over a is equals to sine omega t, this sine omega t, and cos omega t. You can write it as square root of 1 minus sine square omega t, and sine omega t has value x over a, so the value of cos omega t will be root 1 minus x square over a square. This is the value of sine omega t, and this is the value of cos omega t. Sine omega t is equals to x over a, and cos omega t is equals to square root 1 minus x square over a square. This. Okay. Now from equation number 2, from this equation, y over b is equals to sine 2 omega t plus phi. This. Y over b, from this equation, y over b is equals to sine 2 omega t plus phi. So y over b is equals to sine 2 omega t plus phi. And look at this formula. This is actually the formula of sine a plus b. Sine a plus b. So sine a plus b. The formula of expansion of sine a plus b is sine a cos b and cos a sine b. So there is 2 omega t in place of a and phi in place of b. So actually the expansion of this formula sine a plus b is sine 2 omega t, that is sine a, into cos phi, that is cos b, plus cos a, that is cos 2 omega t, and sine b, that is sine phi. So sine a cos b plus cos a sine b. This is the expansion of sine a plus b. Okay. And we also know that the expansion of sine 2a, the formula of sine 2a is 2 sine a cos a. You know that this trigonometric formula, that sine expansion of sine 2a. What is the expansion of sine 2a? Is 2 sine a cos a. And because we have here sine 2 omega t, so the expansion of this formula will be 2 sine omega t cos omega t, this. And look at here, sin 2 omega t is equals to 2 sin omega t cos omega t. This is the expansion of this function, and cos phi is as it is. Okay, so plus sign is as it is, and the formula of cos 2 omega t in the form of 1 minus 2 sin square omega t. This is the expansion of this formula, because in trigonometric expression we have cos 2 theta is equals to cos square theta minus sin square theta. This is the first formula. 2 cos square theta minus 1, second one, and 1 minus 2 sin square theta. Although this is these two are the form of the first function. Okay, so we use here this formula, this one. So cos 2 theta, in place of cos 2 theta we have here cos 2 omega t, and is equals to 1 minus 2 sin square omega t. This cos 2 omega t is equals to 1 minus 2 sin square omega t. We have here. Okay, so use this formula for cos 2 omega t. Use this formula. So look at here. Cos 2 omega t we have here is 1 minus 2 sin square omega t. Okay, and sin phi is same. Okay, so from equation number 2 we have this expression y over b is equals to 2 sin omega t cos phi plus 1 minus 2 sin square omega t and sin phi. Okay, and this is equal to y over b. Now substituting the values of these two functions, sin omega t is equals to x over a and cos omega t is equals to root 1 minus x square over a square into this equation. So y over b, the left hand side is same, is equals to 2. In place of sin omega t we have to put x over a. So x over a here. In place of cos omega t we have value this, root 1 minus x square over a square. So put here root 1 minus x square over a square and cos phi. This plus sin phi is as it is, and sin phi is multiplied in with 1 gives you sin phi minus this function 2 with minus sign 2 sin square omega t, and sin square omega t has value x square over a square. So x over a whole square, and sin phi multiply with this function is giving you sin phi. Okay, so we have this function onto the left hand side and this whole onto the right hand side. So pick these terms, sin phi and this, that is the terms with sin phi. You can say here pick the terms with sin phi. So here is sin phi, here is sin phi, and take them onto the left hand side. So we have onto the left hand side y over b is already there. This plus sin phi when come onto the left hand side gives you minus sign. So y over b minus sin phi, and this minus term when go onto the left hand side, this becomes positive. So 2 x square over a square and sin phi, this. And we have rest of the term, that is 2x over a root 1 minus x square over a square cos phi onto the right hand side. Now you can do this thing, that is squaring both sides. That is square onto the left hand side as well as onto the right hand side. So when you square the left hand side, you have y over b minus sin phi whole square, because this is the square, this will become the square of a minus b, this plus, and the square of this term is square of 2 gives you 4, square of x square gives you x to the power 4, and square of a square gives you a to the power 4, and square of sine phi gives you sine square phi. This is onto the left hand side, plus multiplication of these two terms with double, that is 2 times multiplication of these two terms, that is this formula will become a square, this is square, plus b square, this is square, plus 2ab, so plus 2ab is this term. And onto the left hand side, onto the right hand side, the square of 2x over a is 4x square over a square, and when you square this term, so square is cancelled with the square root, and you have 1 minus x square over a square, and the square of this term will gives you cos square phi. Okay, this, and this term can be written as, if you multiply from the left hand side 4x square over a square into 1, and onto the right hand side this cos square phi. So this term will become 4x square over a square cos square phi minus 4x to the power 4 a to the power 4 cos square phi. This term will become this one. So we have now this whole term onto the left hand side, and this term onto the right hand side. Okay, so do some mathematical analytical treatment here. So y over b minus sine phi whole square is as it is, and look at these terms, 4x square to the power 4 a to the power 4 sine square phi, and onto the right hand side look at this term, 4x to the power 4 a to the power over a to the power 4 cos square phi. What is the common between these two terms? The common is this term. 4x to the power 4 over a to the power 4 is common between these two terms. Okay, so take common from this, and you have sine square phi, and when you take this term onto the left hand side, this term will become positive, and cos square phi will become also positive. So sine square phi plus cos square phi gives you 1. This happened here. 4x to the power 4 over a to the power 4 common, and sine square phi is from this term, and plus cos square phi from this term, when this term is going on to the left hand side. Okay, and look at these two terms, 4x square over a square cos square phi, and with minus sign onto the left hand side 4x square over a square sine square phi. What is the common between these two terms? What is the common? Common is this term, 4x square over a square. Here, look at here, 4x square over a square. So this term 4x square over a square is common here, but this term onto the left hand side with minus sign. So pick this term and come onto the right hand side. So this term will be positive when you take it to the right hand side. So 4x square over a square is common. This here is 4x square over a square is common, and sine square phi will become positive when this term is going on to the right hand side, and onto the right hand side there is already cos square phi. So 4x square over a square sine square phi plus cos square phi. This, okay, this is not equal to 0. This. So we have two terms here, 4x to the power 4 over a to the power 4 common from these two terms, and 4x square over a square is common from these two terms, and rest of the term is same. Rest of the term, that is y over b minus sine phi whole square, is same. Look at here. and 4x square y over a square b sine phi is same. Look at here, and this term is common between this term, and the resultant term has sine square phi plus cos square phi, and you know that this result by trigonometric result, that this bracketed term has value 1, and so also onto the right hand side this bracketed term has also value 1. So the final equation, that is the resultant of the displacement or resultant of the two waves, two harmonic oscillations which are initially perpendicular to each other, have different direction of propagation, have different amplitude, different phase, but frequency ratio into the ratio of 1:2, have this final equation, that is y over b minus sine phi whole square plus 4x square y over a square b sine phi, these two terms, and minus 4x square over a square is come from the right hand side, because this term onto the right hand side is positive, and when it is come onto the left hand side this will become negative, and plus 4x to the power 4 a to the power 4 is equals to 0. This term is same, because sine square phi plus cos square phi will become 1, and sine square phi plus cos square phi will also become 1, equal to 1. So the final equation is this. This is equation number 3rd. Say this is equation number 3rd. So this equation represents the resultant motion of the particle. This represents the resultant motion of the particle. This. Okay. Now discuss about the special cases, because in this topic we are interesting about the path of the particle, and that path, the trajectory of the particle is called as Lissajous figure. जो किसी भी कण का जो परिणामी पथ होगा वो लिसाजियस फिगर हम उसको यहाँ कह रहे हैं, यानी किसी भी कण का, किसी भी पार्टिकल का जो फाइनल ट्रेजेक्ट्री होगा अकॉर्डिंग टू दीज कंडीशंस, दैट इज कॉल्ड एज लिसाजियस फिगर. और जब हम इनको ग्राफिकली प्लॉट करना सीखेंगे तब हम एग्जैक्टली ये जान जाएंगे कि हाँ, कि कैसे हम एग्जैक्टली by the help of these conditions, by the help of this mathematical analysis, we have to plot an exact path of the particle which are filling these conditions, that is, have one SHM into the direction of x-axis, other is into the direction of y-axis, have different amplitude, different phase, and into the frequency into the ratio of 1:2. Okay, so that we'll talk when we start the graphical method of tracing the path of the particle, that is about Lissajous figure. That is, this is the mathematical analysis by which we can obtain these types of figures, and these types of figure is known as Lissajous figure. Okay, this is only the mathematical treatment, clearly the mathematical treatment, or you can say it an analytical method. You can say it as analytical method to get the Lissajous figure, but you can get the exact or original figure by the help of graphical method also. So that we will discuss into our coming lectures, but for the time being let us discuss this mathematical analysis. And this equation number 3rd, represents the resultant path or resultant equation, represents the resultant motion of the particle which have displacement of these types, that is x equals to a sine omega t and y equals to b sine 2 omega t plus phi. These type of displacement. So the resultant motion of the particle is represented by this equation number 3. This equation number 3. This is the resultant path or motion of the particle. So let us discuss first special case when phi is equals to 0. This means there is no phase difference between the two SHM or oscillations which have frequency ratio into the ratio of 1:2, basically have no phase difference. If this will happen, then the value of sin phi is 0. The value of sin phi is 0. So put this result into this equation number 3. Okay, equation number 3 is our resultant equation. So every result we acquire from the special cases, we have to put that result into equation number 3 again and again, and we can get the resultant path by this analytical treatment. We can get the resultant path of the particles. Okay, so from equation number 3 we have, so put sin phi is equals to 0 here. So y over b minus 0, that is y over b whole square, and put sin phi here, sin phi equal to 0 here. So this term will become 0, and these two terms, that is minus 4x square over a square plus 4x to the power 4 over a to the power 4 has no sin phi like term. So these two terms will become same. So here, look at here, y over b whole square minus 4x square over a square minus 4x to the power 4 over a to the power 4 is equals to 0, and you can write this equation as y square over b square minus 4x square over a square plus 4x to the power 4 over a to the power 4 is equals to 0, or you can write it in this way, that is y square over b square plus 4x square over a square into x square over a square minus 1 is equals to 0. This is the resultant equation of the particle, or this is the resultant path of the particle represented by this resultant equation and by this condition, when the phase difference between the two SHMs is 0. That is, no phase difference between the two oscillations which are perpendicular to each other. This is the resultant equation, and this is the resultant path. This is the length 2a, the rectangular. This is the rectangular region, and this is the length 2b, and this is the resultant path of the particle. Okay. Now discuss about the new special case, and that is when phi is equals to pi by 2. So sin phi is equals to sin pi by 2, because phi has value pi by 2. That is, the phase difference between the two displacements is 90 degree or pi by 2 radian. 90 degree or pi by 2 radian. So sin phi, that is equals to sin pi by 2, has value 1. So put sin phi is equals to 1 into this equation. Equation number 3. Put that result, sin phi is equals to 1 into this equation. We have this y over b minus 1. Why minus 1? Because look at here, sin phi is equal to 1. So this term will become y over b minus 1, because here is value of phi, that is the phase difference between the two displacement, is pi by 2 or 90 degree, and sin 90 has value 1. So y over b minus 1 plus 4x square y over a square b Sin phi again has value 1, so this term will become 4x square y over a square b, and these two terms will become will be the same, because these two terms not have the sin phi like term. Okay, so look at here, y over b minus 1 whole square plus 4x square y over a square b into 1, because here is sin phi and sin phi has value 1 according to this condition, minus 4x square over a square plus 4x to the power 4 over a to the power 4 is equals to 0. Okay, and y over b minus 1 whole square is same, this term will same, and look at these two terms, this term and this term has common 4x square over a square, and this term also has 4x square over a square. So 4x square over a square, this term is common from between these two terms. So take common 4x square over a square, and you are left with y over b and minus 1 here, and plus 4x to the power 4 over a to the power 4 will be same, equals to 0. Okay, and now look at this equation, y over b minus 1 whole square plus 4x square over a square into y minus b into 1 plus 4x to the power 4 over a to the power 4 equal to 0. And if I write this term as 2x square over a square whole square, this term, can I write it? Can I write it this term in this way? That is, if I write this y minus b, y over b minus 1 whole square plus this term is same plus, and this term 4x square x to the power 4 over a to the power 4 can be written as 2x square over a square whole square. And look at this term, 4x square over a square and y minus b. This term is 4x square over a square and y over b minus 1. This. So can I write it in this way again? Let us just simplify it. Y over b minus 1 whole square plus, can I write it, 2 y minus b minus 1 and 2x square over a square plus 2x square over a square whole square. So look at here, a square in place of a square plus 2ab plus b square. In place of a, here is y over b minus 1, so a square plus 2. In place of a, this is a, and in place of b, this is 2x square over a square, 2x square over a square, and square of this. So this can be write as a plus b whole square, and you can write that equation, this equation, as y over b minus 1 plus 2x square over a square whole square. So look at here, look at this result, look at this result, y over b minus 1, okay, plus 2x square over a square whole square, and look at this result, this y over b minus 1 plus 2x square over a square whole square, y over b minus 1 plus 2x square over a square whole square. These are same result. So this equation can be written in this form. This, and because of whole square, we can write it as y over b minus 1 plus 2x square over a square equal to 0, or y over b equals to 1 minus 2x square over a square, or y over b is equals to multiply this a square into 1, so a square minus 2x square over a square, or you can write y is equals to minus b over a square 2x square minus a square. Take a minus sign common from this numerator term, so why this minus is here, and this will become y is equals to b is cross multiply minus b over a square, and this term, because of common of minus sign, 2x square over a square. This term will become in this form. Okay, so this equation represent a parabola and shown in this figure. This is again a rectangle which have length equals to 2a and breadth equals to 2b. Okay, so in the same fashion as we did in our last lecture, if we regularly increase this, that is the phase between the two displacement or two SHM or two oscillations represented by these two equations, and if we constantly increase the phase between these two displacement or these two SHMs, so we can finally get these types of Lissajous figure. These are only two examples. When phi is equals to 0 and when phi is equals to pi by 2. You can put here phi is equals to pi by 4. You can also put 3 pi by 4, pi, and so on. These all values. That is, you can put 0. We solve the case of when phi is equals to 0. And you can put here phi is equals to pi by 4. You can put there. And phi is equals to pi by 2. We already solved this case. Phi is equals to 3 by 4. Another case. Phi is equals to pi. Another case. Phi is equals to pi by 4. 3 pi by 2. 7 pi by 4. 2 pi. And you regularly get the Lissajous figure. But at some time later, these figures are repeated itself, because look at here, this figure is repeated by this figure, although the quadrant are different, but this is the equation of a straight line, and this is also the equation or figure of a straight line. This and this is same, although the quadrant is different. This and this is same. This and this is same, although the quadrant is again different. And this and this again the equation of a straight line, although into the different quadrants. Okay, so these are the results we can acquire by making the phase different between the two displacements. Okay, and you can find these types of resultant Lissajous figure by putting the different value of phi into this resultant equation number 3 in this topic. So Lissajous figure obtained under the action of two SHMs having different amplitudes, phase and frequencies in the ratio of 1:2 is showing in this figure. So this is the case of phi is equals to 0, that is that there is no phase difference between the two waves, and the resultant figure is in this shape. When phi is equals to pi by 4, the resultant figure in this shape. Phi is equals to pi by 2, we already solved this case. So this phi is equals to 3 pi by 4, this case. This is the same path of the particle as when phi is equals to pi by 4. Phi is equals to pi, this and this will be same. Phi is equals to 2 pi, 3 pi by 4, 3 pi by 2, pi by 4, and so on. Okay, so these all are the resultant path or trajectory of the particle which have displacement given by equation number 1 and 2 in this particular topic. These are the all called as Lissajous figure, and these figures are the resultant trajectory of the particle under these conditions, under these mathematical analysis. Okay, so this is the mathematical analysis, or you can say it as analytical method to obtain the Lissajous figure. There is another method by which we can obtain the Lissajous figure, and that is by the graphical method. By the graphical method. So let us see this. This is the graphical method for tracing Lissajous figure. Okay, and for tracing the path or resultant path of the particle by this method, we have to make some considerations. Okay, and the considerations are these. This is the graphical method of tracing Lissajous figure. Okay, and the nature of resultant path or the curve traced out depends on the amplitudes. What are the amplitudes between the two displacements? What is the time periods or frequencies between the two waves or two SHMS, and the phase difference between the two components vibrations. Okay, and you can trace the resultant path by this graphical method for the two SHMS which are perpendicular to each other. Either they have same frequency or frequency in the ratio of 1:2, or in the 1:1. There is no effect by this method. The figure is same. You can draw the Lissajous figure for the resultant of the two SHMS which are perpendicular to each other. The basic is this: must be perpendicular to each other. So two SHMS or harmonic oscillation must be perpendicular to each other. That is, if one is going into the direction of x-axis, other should be going into the direction of y-axis. This is the consideration, and these are the dependent terms. If amplitude is same or not, time period is same or not, or you can say it is frequency is same or not, or phase differences exist there or not. Okay, so these are the dependent quantities. Okay, so let us discuss first case where amplitude different, period or frequency same, and phase difference is pi is equals to 0 degree. Okay, this, and first let us describe or look at this case by what is the resultant path of the particle when we discuss this case by the analytical or mathematical analysis. Let us first take a look at that. When amplitude different, period or frequency same, and phase difference is pi equal to 0. So this is the case. Yes, this is the superposition of two perpendicular harmonic oscillation having same frequency. That is the frequency ratio into the ratio of 1:1, and the case is this. When phi is equals to pi, so the resultant path of the particle, is this: y over b plus x by a whole square, or which represents a pair of coincident straight lines lying in the second and fourth quadrant. This This is the resultant path of the particle. Okay, when the two harmonic oscillations perpendicular to each other have different amplitude, same frequency, and phase difference equals to pi radian. This is the resultant path by mathematical analysis. And what is the resultant path of this particle by graphical method? So let us see that. This. So this is the condition, that is amplitude is different, period or frequency is same, and phase difference is pi radian. So the resultant path by the mathematical analysis, as we find earlier, is a straight line lying into the second or fourth quadrant, or whatever the quadrant is. Okay, so this. So when we have the equation of displacement of two SHMS perpendicular to each other under these conditions, that is x, the displacement of the particle into the direction of x-axis is given by this equation, and y is equals to b sin omega t plus phi is the displacement of the particle into the direction of y-axis, and because phi equal to 0, there is no phase difference between these two displacements. So this equation will become y is equals to b sin omega t, phi equal to 0. Put phi equal to 0 here, so this equation will become this. Okay, let the simple harmonic vibration along the x-axis have an amplitude equals to a, and the vibration along the y-axis has amplitude b, as shown in these figures. Okay, draw two circles of reference radii a and b. That is, draw two circles of reference radii a and b, that is the radius of the circles which we trying to draw here is equal to the amplitude of the two displacement. Okay, that is the displacement, this displacement equation have amplitude equal to 1. To draw a circle of radius is equals to a, that is equal to the displacement of amplitude of this equation, and another circle which is equal to the amplitude or peak amplitude of this displacement equation equals to b. So draw two circles of reference radii a and b equal to the amplitudes of the corresponding SHMS taking place along the x-axis and along the y-axis. So because this equation represents a SHMS which is take place into the direction of x-axis, and this equation represents a SHM which propagating along the direction of y-axis. Okay, now in the circle of radius a, that is this, draw a diameter xx prime or xx dash parallel to the x-axis. This is another important thing, because this oscillation or harmonic oscillation is propagating into the direction of x-axis. So draw the diameter of circle of radius a into the direction of or parallel to the x-axis, and in the circle of radius b draw a diameter parallel to the y-axis. Okay, because this displacement is into the direction of y-axis. As the period of frequencies are equal, divide the both circles into an equal number of parts, say 8 भागों में हम उन्हें divide करेंगे, so that each part traveled into the same time. जब equal part होंगे तो जितना समय वो लेंगे एक path को travel करने में, उतना ही दूसरे में भी लेंगे. So draw these lines through these points, perpendicular lines to the diameter xx prime and yy prime respectively, so as to enclose a rectangular PQRS. So these verbally discussion is plotted in the form of graph here. Okay, let us now understand what happened here, we have two equations of displacement. X is equals to A sin omega t and Y is equals to B sin omega t plus phi. Okay. One, because phi between the two SHMS we consider as 0 degree, or so this displacement will also become as Y is equals to B sin omega t. What is the difference between these two displacement equations? The difference is that this displacement is along the x-axis and this displacement is along the y-axis. The amplitudes are different. So the first thing is coming from here. Amplitude. This has amplitude, this equation has amplitude A equals to 1A, and this equation has amplitude equals to B. To draw a circle of radius A and radius B. So let us see here. This is the circle of radius A and this is the circle of radius B. This is the first thing. This is the first thing which have to become in our mind. Draw a circle equal to the radius of amplitude, equal to the radius, which is equal to the radius will be equal to the amplitude of the displacement equation. Here is amplitude equals to A, so why we draw a circle of radius A. Here is amplitude equals to B, we draw a circle of radius B here. This is the first thing. Okay. The second thing is draw the diameter of this circle, and this diameter should be parallel to should be parallel to this diameter x prime, should be parallel to the x-axis. Why should be parallel to the x-axis? Because this wave is traveling towards x-axis. And the second diameter should be parallel to the y-axis. This diameter y prime should be parallel to the direction of y-axis. Why parallel to the y-axis? Because this displacement is into the direction of y-axis. So why this displacement is parallel, or this diameter is parallel to the direction of y-axis. This is the second thing. First thing is draw a circle equals to the amplitude of the two waves. First circle have radius equals to A, and second circle have radius equal to B, which are the amplitudes of the two displacement equations respectively. Okay. Second thing, draw the diameter of two circles. But remember, the diameter of the circle, x prime should be parallel to the x-axis for the displacement of this equation, and this diameter should be parallel to the y-axis, because this circle represents the displacement of a particle into the direction of y-axis. Okay, complete this. Now divide these all the two circles into equal parts, and you can divide it into equal parts, say 2, 4, 8, 16, okay, 32, whatever you want. But the precise method is to divide these circles into 8 equal parts. Why equal? Because we have same frequency, and same frequency, that is, if I divide it from 0 to 1, that is path traveled from this to this, the time taken to travel this path is equal to time traveled from this to this. Okay, so this is the concept behind that. Now draw the projection. And projection of what? Draw the projection of every point, and meet which look at the point of intersections of these projections. Okay, so the method is that draw the projection of center first, that is from here. Draw this projection, and draw the projection of center from here. Okay, this will meet here. Again, draw the projection of diameter. This is the projection of diameter, and draw the projection of this diameter, this and this, and at the intersection of the projection of diameter, these projection or intersections encloses a rectangle shaped figure. This arm is 2a and this arm is 2b. Why 2a? Because this length is equal to this diameter, and this length is equal to this diameter. That's why this arm of rectangle will become 2a and this arm of rectangle will become 2b, because this will be equal to this 2b, the radius of this diameter, the diameter of this circle, and this will become 2a will become equal to the diameter of this circle of radius a. So the projection of diameter of two circles will enclose a rectangle of arm 2a and arm 2b. And the next task is to draw the projection of every point, and check the intersections of that point. Check the intersection of that point. Okay, so let us draw that. So look at here. Starting from the first point. Let us make it clear to you. This is okay now. Okay. Yes. Okay now. Now look at here. This is we proposed that this circle and this circle will be divided in equal parts. So I divided it into equal parts: 0, 1, 2, 3, 4, 5, 6, 7, and 8. 8 equal parts. And look at here: 0, 1, 2, 3, 4, 5, 6, 7, 8. 8 equal parts. Okay. So draw the projection of every point and trace the intersection of projection. So look at here. 0 is here, and because this diameter is along y-axis and this diameter is along x-axis or parallel to x-axis, the first point of this circle will start from this, and the first point, that is 0 point, is start from this. Okay, because these are two perpendicular displacements. Perpendicular, this 90 degree. So draw the projection of 0 first. So 0 is this point, and draw the projection from here, 0, this point. So we'll meet at this point. Draw the projection of 1. This is projection of 1, this, and this is the projection of 1 point of the circle of radius p. So meet here. Draw the projection of 2, this, and here draw the projection of 2. Will meet here. Similarly, projection of 3, projection of 3, projection of 4, projection of 4 here. So we start from this point and come onto this point. Now draw the projection of point number 5 of circle of radius A. So phi is coincide with the projection of point number 3, and here is similarly the projection of point number 5 is coincide with the projection of point number 3, and this will meet at this point. Again, the projection of point number 6 of circle of radius A will coincide with the projection of point number 2 of the same circle, and here is same also. The projection of point number 6 will coincide the projection of point number 2 of circle of radius B, and these projections will meet at this point. Similarly, projection of point number 7 here, projection of point number 7 here, and projection of point number 8, and projection of point number 8. This. So the resultant path of the particle, when you connect these all points, you can get or you will get a straight line. So particle which performing SHM first start their SHM from this point, come on to this point, and then again reaches to the initial point. In this way, this particle will perform SHM in this way. Start SHM from this point, come on to this point, and again reaches to the same point. In this way, this particle will perform its SHM. Okay, so this is the first example. We have to study another examples of different cases into our next lecture. Okay, so meet you into the next one, and thank you for now.